Because only 0.7% of natural uranium is the chain reaction forming 235 variety, thorium is actually nearly 500 times more abundant.
Nope, wrong. Horrible analogy. I'm sorry. That's just so bad. Hey everyone, I'm Charlie Murphy. I'm a nuclear engineer, and today I'm here to answer the question, is thorium going to save the world? And the answer is no. All right, thank you all for watching. See you guys next time. No, just kidding. Today we're going to be looking at this video that claims that thorium is here to save the world. And while I do think thorium is cool and definitely has some promising aspects to it, I do not think it is the silver bullet that the nuclear industry is waiting for to save it. So I will address certain claims that I think need addressing or explain things that I think need explaining. But before we get started, a disclaimer. I work for Westinghouse Electric Company, but I am not here representing Westinghouse Electric Company.
Their design, a molten salt reactor running on fuel bred from thorium, ran successfully for 15,000 hours from 1965 to 1969. So why don't we have this limitless thorium energy today? Because the project was defunded after the Atomic Energy Commission shifted its research focus to a different kind of breeder reactor, which too was plagued by technical challenges until its own cancellation.
So thorium got canceled. Why did thorium get canceled? Initially, in the early days of nuclear engineering, the 40s and 50s, it was thought that uranium was pretty scarce. And that, it would run out pretty soon. And, uranium is how we power all our nuclear plants today. It turns out there's a lot more uranium than we thought there was. So on the whole, uranium is cheaper than thorium. So that is why thorium got canceled and uranium stuck around. The Clinch River breeder here that was talked about wasn't really elaborated on, but this was going to be a plutonium breeder. Breed uranium into plutonium, which is also another kind of breeding that can be done. Thorium is not the only thing that can be bred. It's a weird tense I'm not really too familiar with when it comes to talking about nuclear breeding. The main reason that breeding, without getting too far ahead of ourselves, but the main reason that breeding is not pursued is because it is more expensive than the once through uranium cycle. But this Clinch River breeding program was also canceled in part because of proliferation concerns, but also because of monetary concerns, because our current system is cheaper than breeding. I don't want to get too ahead of myself, so let's continue.
Copenhagen Atomics is a startup out of Denmark, reviving Weinberg's hopes for a so-called breeder reactor, one that creates more fissile fuel than it burns.
So it is not presently clear that breeder reactors themselves can be profitable. What might be more likely is a system where you have a breeder reactor that then makes fuel for a bunch of other burner reactors. It's not clear that you could have an entire nuclear power system that is only made up of breeder reactors. Now that may be more of a traditional non-molten salt kind of situation, because with this molten salt reactor, in theory, you can pull the new fuel out while the reactor is running. With more traditional types of breeders, I'll say you have to shut down the reactor, or at least remove a whole fuel assembly from the reactor, this fixed object. And then you have to do very intensive, expensive chemical processing to separate out this new fuel you made. And then you have to formulate that into new fuel assemblies that can go into other reactors. But the promise of this thorium molten salt reactor is that all this can kind of be done on site, because there is no, as we're kind of getting ahead of ourselves a little bit here, there is no like structural fuel. It's all a liquid, which is very, very exotic compared to what exists out there now for nuclear power.
And when I say small, I mean Copenhagen Atomics reactor is designed to fit inside of a standard 40-foot shipping-sized container. And by modular, I mean they aim to mass produce one reactor per day on an assembly line, then truck as many as needed to a plant site to hit the desired power output.
So the fit inside a shipping container thing is definitely a little bit of a misnomer, I think. We'll get into that later, but it's not telling the whole story. And then one reactor a day sounds very, very ambitious. The United States, which is the world's largest nuclear power producer, not the largest nuclear power share, but the largest nuclear power producer by raw gigawatts, has only ever made just over 100 power-producing reactors. So, bold aspirations for sure.
And because they're building the same design over and over, they can work out the kinks in the manufacturing process, which means delivering reactors at a predictable cost instead of the massive overruns that have plagued large, custom-built nuclear power plants.
Okay, let's talk about all these terms that are flying around here. We got modularity, we got standardized designs. These are all things that are, on paper, are things that should make nuclear power cheaper. So pretty much all the nuclear power plants in the world are Generation 2 nuclear reactors. What this means is these were all reactors that were built in the 60s, 70s, and 80s. And yes, as our host Matt here said, they were all custom built and custom licensed. Each reactor had its own. This is when you build a nuclear reactor, you have to go to your nuclear regulator and you have to get it licensed. The nuclear regulator is very involved in these processes. So at least, in the United States, each reactor that was built had its own separate design and its own separate license, and the power plant was its own custom design. Very intensive and, not ideal to do all that custom work. Starting, back in the 80s or 90s, the nuclear industry saw the advantage of going to like a standardized kind of design. And that is what we have nowadays. This stock footage that they were just playing was showing the 2 new Westinghouse AP1000 reactors at Plant Vogtle in Georgia. And those are a standardized design. I think it was the first reactor to be licensed by the NRC in this manner, where the design is licensed. So if anyone else wants to build AP1000 reactors, they do not have to license their reactor design anymore. That is already done. That's not the whole process, but that's a significant chunk of it. So, this standardized design thing is something that has already been, addressed, and small modular reactors are supposed to be, modular. But you can have a large modular reactor. Nothing saying you can't. Module doesn't mean small. Module just means, it's interchangeable pieces, and, it's not proprietary design like those old Generation 2 reactors. Standardized design, interchangeable parts, interchangeable modules.
The Nuclear Energy Agency estimated that worldwide uranium reserves will only power us for another 200 years at current consumption rates.
So it's worth noting here that thorium is not the only thing that can be bred. I think I mentioned this earlier, but uranium can be bred into plutonium. And when you do that, the reserves of uranium that exist can last for so much longer. So it's not just a thorium thing. It can also be a uranium thing. But, something that is, rather, I guess I'll say theoretical or, cutting edge at this point is what is called seawater extraction of uranium. So the ocean actually has a lot of uranium in it. Don't worry about swimming in the ocean or not swimming in the ocean. It's very dilute. It's always been there. But in theory, saltwater or seawater extraction of uranium is something that could be done. And there's actually more uranium than thorium in the world when you consider the amount dissolved in the ocean. But, that technology is nowhere near being mature or anything like that. But, just food for thought there.
However, there's a solution to uranium scarcity, and that's another element, thorium. It's not only 3 to 4 times more common in Earth's crust, because only 0.7% of natural uranium is the chain reaction forming 235 variety. Thorium is actually nearly 500 times more abundant.
Nope, wrong. Horrible analogy. I'm sorry. That's just so bad. Thorium. So he's talking about there's only 0.7% fissile in natural uranium. That is correct. That other 99.3% is non-fissile uranium-238. Well, that thorium that he's talking about is 100% non-fissile. So what is that 500 times number? That is wrong. Completely wrong. He corrects this in a second here, but that is just, I don't know what the point of that stat was. All thorium needs to be bred into fissile material, which is uranium-233. Uranium has fissile material in it already. That's why it can be used to power something like a CANDU reactor, which is short for Canadian Deuterium Uranium Reactor. It runs on natural uranium. American reactors do not. They need enriched uranium, as do most other reactors in the world. But that, I don't like that comparison at all.
Now, thorium can't form chain reactions like uranium-235. But if thorium is seeded with a little uranium-235 or plutonium-239, which are both fissile materials that release neutrons when they split,
yes, you have to seed thorium-232 with a fissile material, whether that's uranium-235 or plutonium-239. And where did that plutonium-239 come from? It came from breeding uranium-238. So this is where like my big hold up with thorium comes from, is that you can breed uranium into plutonium. The main reason that people think thorium is better than that, we'll get to later, but it's one of the big myths around thorium that needs to die.
So instead of burning up an ever-dwindling supply of nuclear fuel, or even burning up as much fuel as it makes, the thorium fuel cycle lets us breed more nuclear fuel than it consumes.
So this is all like contingent on the fact that there would never be uranium breeding. So of course, there's all this uranium if you could breed it into plutonium-239, the same thing that is going on with thorium here, you can claim. The advantage that thorium has is that you can breed it in what we call a slow reactor. So all the reactors in the world that generate power, pretty much all of them, are what we call slow reactors. They have a neutron moderator that slows down neutrons. And this means that it's cheaper. It means you can have cheaper fuel. You don't have to enrich the fuel as much, which is the concentration of fissile. The more you have to concentrate, the more expensive it is. But so with thorium reactors, you can breed them in a slow environment. For uranium breeding into plutonium-239, you have to breed them in a fast environment. So a fast reactor. Fast reactors have their own host of issues. Slow reactors were chosen for a multitude of reasons, including primarily because of the lower enrichments. A fast reactor, you generally need about need a lot higher enrichment on your uranium to actually light that thing off, as you say. So yeah, uranium can be bred into plutonium, but you have to do it in a fast reactor, which the US has never really had, at least on that kind of scale, to breed uranium into plutonium. The reactors that did it during the Cold War and the Manhattan Project were different, and they probably are not economical at all. I'm sure those were just like, that was for making weapons stuff, but some kind of commercial fast breeder reactor, which would be a completely different design than those Cold War reactors too. Those were all slow reactors with moderators. A fast breeder reactor would have to be economical of some sense. And then with the uranium side, the thorium advantage here is that molten salt aspect. The fuel can be made on site and put back into the reactor. With uranium breeding into plutonium, you have to take that fuel out of the reactor and do what we call reprocessing, which is rather difficult, expensive chemical processing to remove and separate that fuel to then be made into a new fuel for another reactor, for other reactors.
If you really want to have 10 or 20 or 100 times more energy on this planet, then we need what is called breeder reactors.
It's a good point brought up there by the Copenhagen Atomics CEO. If we are to be on the cusp of a nuclear renaissance and we're going to start building, 10 or 100 times more the nuclear generating capacity than we have right now, breeding will have to quickly become part of that equation, because depletion of current stocks would be a significant concern. And I don't think I could have said that more jargony or dry just then.
MSRs are powered by uranium and thorium dissolved into molten salts. Because the fuel is liquid, waste products from nuclear fission can be extracted with the reactor still running. Liquid fuel salt acts as a coolant too, circulating out and back into the reactor core to deliver heat for the power generation.
When you have liquids, you can actually separate these things out. And it's a mix of chemistry and electrochemistry to do that, but it's a completely autonomous system that runs inside the reactor while the reactor is operating.
Watching the description here of the reactor, there's like a tug of war going in my head here with aspiring nuclear engineer being like, oh yeah, so cool, new stuff. And then like me, 12 years in the industry, nuclear engineer being like, oh, well, we have this proven technology, money, proven capability. So what I mean by that is all these water reactors in the US have, maybe it's the whole world, have like a combined, tens of thousands of years of operating experience. And that's, how long all these reactors have been, operating, added together. The beginning of the video mentioned that the molten salt reactor experiment had like 15,000 hours. Well, with all these water reactors, it's, more like 15,000 years of combined operating experience. So that doesn't come for nothing. Let me put a little chart on the screen here, and this shows the uptime of nuclear reactors as a function of time. So what that means is, as we've progressed through the decades here, water-based nuclear reactors have higher and higher uptimes. And you could say that one way to interpret this chart is that it's taken us 30 or 40 years to really understand how to operate these things efficiently, effectively. It is a credible thing to say that that kind of learning curve would have to be applied to any kind of new reactor technology, whether that's any flavor of small modular reactor or a fast breeder. It's likely some kind of long-term learning curve like that would have to happen to really, squeeze as much potential out of those reactors as possible. Because this is all unproven technology. The first time we turn this thing on, we're going to learn so much about these and things that we had not thought about that will have to be addressed. And this isn't like, we're not talking about meltdowns and such. We're talking about routine things like, how does this pump react to this salt at this temperature? How does this pressure vessel react to this salt at this temperature, kind of thing, in the case of this molten salt reactor. So that's not to say these technologies should not be investigated and pursued, but we don't need this either or approach. We should be, focusing on tech that already exists and building that out while also working on newer tech that can address different aspects of the market, or perhaps even expand nuclear's presence overall.
Another massive advantage of MSRs is that unlike traditional water-cooled reactors that operate under high pressure to keep the water from boiling, molten salt reactors run at atmospheric pressure. That means no risk of high-pressure steam explosions and sudden loss of coolant or rapid overheating if a breach occurs. Many designs, like Copenhagen Atomics, even include frozen plugs at the bottom of the reactor vessel. If the system overheats, the plug melts, and the molten salt drains by gravity into a shielded dump tank, passively shutting down the reaction and preventing a meltdown.
So steam explosions with the water reactor is a valid concern. That is certainly a valid concern. And so are meltdowns with a water reactor. But a lot of work has gone into making these reactors, very resistant to meltdowns. Newer designs are much better at this with fully passive safety features that include this, walk away capability. Older reactors have had tons of years of experience and knowledge applied to make them safe. Fukushima was, without derailing this conversation too much, a bit of a fluke, and that sounds flippant, but all the other reactors in Japan did not have meltdowns that were along that Pacific coast. So, Fukushima, those generators, which were the cause of that meltdown, should have been above the predicted water table there. But that's a conversation for another day. And then Chernobyl, that was a bad design. That should never have been built. But again, conversation for another day. The inherent safety of some of these new designs in terms of meltdowns is definitely something that is laudable.
While thorium reactors are walk-away safe, they're not exactly walk-up safe. A small amount of uranium-232 forms during the production of uranium-233 and gives off intense gamma rays powerful enough to pass through centimeters of lead. That makes uranium-233, which could otherwise be an ideal bomb material, a logistical nightmare to steal or weaponize.
All right, so this is the myth of thorium breeding that will never, well, hopefully we can get it to die starting today, but has persisted and will not go away, and that is that somehow that thorium fuel cycle is inherently proliferation proof. So what does proliferation mean? It's basically, in this context, it's giving nuclear bomb material or nuclear bomb technology to countries that don't already have it. Whether or not that's what should be the benchmark for nuclear weapons is a whole other conversation, and we're not going to get into that today. What Matt was saying here about some uranium-232 being made during this breeding process is correct, and it is indeed a strong gamma emitter. And so what that means is, like you said, it gives off a lot of radiation that could make handling nuclear bombs more difficult, but not impossible. Certainly not impossible. What would make thorium, inherently proliferation proof is if it didn't make fissile material, which would defeat the whole purpose. Uranium-233 is a material that can sustain a chain reaction, just like uranium-235 or plutonium-239. That's why this reactor works, and that's why nuclear bombs can exist. You can't separate that fact. What would make it, because proof is like a strong word in nuclear, and I may be projecting my own nuclear engineering conservatisms onto this, but proof is a very strong word. Proliferation proof. To me, that would imply inherently impossible, which would be like trying to make a nuclear bomb out of oxygen or something. Yeah, that's impossible. But the uranium-232 is a valid concern depending on what type of thorium, what thorium fuel form factor we're talking about here. So thorium can't only be used in a molten salt reactor. You could have like a triso pebble bed reactor. This is a new reactor type it's an old reactor type that's being investigated currently. So these triso reactors were initially envisioned to be thorium breeder reactors, and in that instance, the uranium-232 would become a proliferation concern because it's going to be commingled with the uranium-233, and there's no way to separate that chemically because they're both uranium. They're different isotopes, but the chemicals, they look the same, so it's impossible to separate chemically.
This continuous cleanup keeps the thorium to uranium reaction humming along by preserving neutrons for fuel production instead of letting them get soaked up by the waste. And the outer layer of the onion will be a breeding blanket, where additional thorium salts will absorb neutrons produced by the chain reaction within the reactor core, breeding uranium-233.
Now, the thing that makes this thorium molten salt reactor work with the isotope separation, or with the element separation that was talked about earlier, is precisely the thing that would allow this to be a proliferant. So in your thorium molten salt reactor, when that thorium-232 is hit with hit with a neutron and becomes protactinium-233, you want to then remove that protactinium-233 from your reactor right away. It's a strong neutron absorber, which is not good for your chain reaction. And if that protactinium-233 absorbs a neutron, it will become protactinium-234, which is not fissile, won't ever become fissile, won't do anything useful for you. So you want to pull that protactinium-233 out as soon as it's made. Once that's pulled out, you can pull that out separately from the uranium-232 because they're different elements, right? So they're different chemical interfaces that can interact with them separately and not interfere with each other. So then that protactinium-233 will then decay into uranium-233, and there you have your pure fissile material that is radiation-free and ready to make bombs. So yeah, I don't know why this doesn't get more attention or why everyone kind of goes along with this, but you can certainly proliferate nuclear bombs with U-233. Even if it was contaminated with U-232, I think that would just make it more inconvenient, but I don't think that would stop someone from making a bomb with it. It doesn't make it impossible to work with, it just makes it trickier. And of course, you'd rather just use uranium or plutonium at that point anyway.
However, it also means that Copenhagen Atomics will have to go to great lengths to keep that radiation contained. The plan is to avoid sending humans anywhere near the reactor containers. Each unit will be sealed in a steel box at about a half a meter or 20 inches thick that will weigh in at 1,000 tons.
So designing it so that a human never has to get in touch with it sounds like a good idea, but things will always break. It's been a while, but I think I heard that this is being designed so that, remote maintenance can be done easily, or at least it's being thought about. But it's always, trying to have some system where it's humans will never, assuming humans will never have to get near it can be tricky. Stuff breaks, stuff can happen.
Remotely operated cranes and forklifts will handle the heavy lifting, keeping the process as hands-off as possible in order to cut down radiation exposure and red tape all in one go.
So what if that crane breaks? Is there some area for it to go where it can be worked on down that track? Is there going to be maintenance that has to be done to that crane track? So these are all things that have to be kept in mind, like areas where humans don't have to get to do maintenance becomes quickly. Usually those ideas tend to be scrapped, and the cost savings that was going to be associated with it goes away. So nothing is going to happen here, but these are just things that have to be kept in mind.
Nuclear waste from thorium reactors is actually much easier to manage. That's because fission products from traditional uranium-235 reactors includes plutonium and other elements that stay dangerously radioactive for tens of thousands of years. The waste from uranium-233 bred from thorium, on the other hand, decays much faster. It's kind of like choosing paper or plastic at the checkout lane, because instead of needing to store spent uranium fuel underground for tens of thousands of years, or even 100,000 years, thorium reactors' waste can often be safely stored above ground for just a few hundred years.
So all that kind of waste from a traditional reactor with the uranium fuel cycle, if you were to make plutonium breeding as an option with fast breeder reactors, you could burn that same waste that we're talking about here in that fast breeder reactor, that tens of thousands of years waste, and reduce the lifetime to that same hundreds of years waste that was talked about here. So in addition to that, while the U.S. is looking for a deep repository right now, all this spent fuel in the U.S. is currently being safely stored on reactor sites right now. And all this waste from the entirety of U.S. nuclear power production could fit in a football field sized area. So it's not really as much waste as one may think it is, and it's in a much more safe and stable form than something like The Simpsons would lend you to believe. It's solid. It's in the form of fuel assemblies. It's not goop. And then, once all that short-lived waste decays away, the long-term waste is, not as dangerous, because it's, the whole fact that it stays radioactive longer means it's less radioactive, if that makes sense. Radioactivity is just means atoms are unstable and they're giving off energy. So if something is more radioactive, generally it has a shorter half-life. It gives all this energy really quickly. The long-term stuff like uranium or thorium is not very radioactive because its half-lives are very long. Like thorium has a half-life of like 13 billion years, and that makes it one of the least radioactive substances because it gives off that energy so slowly. That's what the half-life tells you. So once all the dangerous short-lived stuff, which is the fission products, which comes from splitting the atoms, once that's all gone, you have relatively low danger radioactive waste left behind. So yeah, it lasts for a long time, but is it any more, is it much more dangerous than the uranium or thorium that exists in the ground? And then, of course, if we get, if fast breeder reactors ever become a thing, they can burn that waste too, so.
But it's not just the heat or corrosion, it's the neutron bombardment from the core that slowly wears down materials at an atomic level. And because the core also blasts out intense gamma radiation, these systems can't be serviced once the reactor is up and running. They have to work flawlessly for years, more like a sealed battery pack than a conventional machine.
So this is where I kind of want to get like a little tangential, not terribly so, about, the nuclear industry and, kind of one aspect of like engineering in general that's kind of happened in the past few decades with the advent of, computer design and everything like that. Maybe it's just me, but I feel like the bean counters and the engineers are always kind of button heads a little bit. So like digital design softwares like CAD and Autodesk like that, what they really get you is the ability to design systems and structures that just use less material than they did back in like the 50s and 60s, say, and get you the same performance. So like, for example, you could make maybe like a bridge, have like 50% material, but have the same strength and lifetime as a bridge that was designed much longer ago. That's just like an example of what digital design gets you. That's like an extreme example, but that's really what it gets you. Some point along the way, someone who didn't know any better thought that you could use these kinds of tools to avoid having to do testing or prototyping, And while these these digital design tools can let you develop very intricate systems as well, very interconnected, intricate, kind of modular systems that you can stick together, like new submarine construction, for example. They certainly do not replace prototyping and testing. That's one thing. If I did not make this clear, I'm not in this video to attack Copenhagen Atomics or anything like that. Just trying to dial back some of the hype on thorium. But what I will most certainly applaud Copenhagen Atomics and Kairos Power here in the United States for, I'm sure with other startups, is that they are focused on doing prototyping and testing and getting real world experience with all these things, and taking a methodical, realistic, stepwise approach to developing these things, as opposed to, I'm sure, like other nuclear startups that have existed and since shuttered their doors, that had something on paper and promised the world and then had nothing to show for it, or had no plan to do any kind of practical testing. Like, practical testing needs to be done. Things need to be turned on and manipulated, and things need to break, and experiences need to be gained. So that is something I do want to applaud greatly here. Is this this needs to happen? Like, if these technologies are going to be actually implemented, we need to know how these systems are going to work and potential kinks and getting them up and running. So something I want to encourage and support, and yeah, it's the right way to go.
The steel can endure corrosive salts and neutron bombardment for at least 5 years, after which the reactor module is shut down and swapped out for a fresh one. That's right, just 5 years. In traditional solid fuel reactors, corrosion and radiation mostly wear down the fuel rods and their cladding, which are components designed to be swapped out during routine refueling. But in molten salt reactors, the fuel is dissolved into the circulating salt, which flows through nearly every part of the system. That means the entire reactor module, core, pumps, and pipes takes the hit.
That 5-year number is interesting because that's, for traditional fuel, like Matt was just talking about, it pretty much lasts about 5 years as well. Traditional fuel assemblies, they get moved around in the reactor two or three times, but yeah, they last about 5 years as well. Very interesting. I don't mean anything. I don't mean to imply anything with that. I just find that only engineers say interesting in a non-ironical way. And it's also worth mentioning, to kind of go back about like maintenance or whatever, this is also an interesting problem with the molten salt reactors, is that the fuel is in the entirety of the reactor. All those pipes and diagrams that we've been seeing, fuel, aka radioactivity, will be in every single part of those things. So even when the reactor is shut down, you still can't get near it because the radiation is too high. With current traditional water reactors, all that fuel is fixed, it's solid, it's fixed in place in the middle of an enormous reactor vessel surrounded by water. This reactor vessel is like 6 inches thick, 15 centimeters or so. When the reactor's running, no one can get near it with the traditional reactor. But when you shut it off, people can get near it and do maintenance on all the pipes and stuff, because there's no fuel in those pipes. There's just water in there. So that is a challenge with the molten salt reactor, is that all those things that may need to be worked on will be full of highly radioactive stuff. And that makes maintenance more or less, that makes it very difficult. I'm not going to say impossible, I'm not going to say the I word, but it makes it very difficult, which means expensive.
Even with frequent reactor swaps, Copenhagen Atomics still sees a path to low-cost power, and Peterson is quick to note the upside.
But the great thing about that is that every 5 years you are able to upgrade your technology, whereas now with the classical nuclear reactors, they run for 50 or 60 years, and it's still the old technology from back in whenever they were built. But in our case, we will keep on, even after 50 years, it's still 5-year-old technology. So that's sort of a plus in terms of keep on improving the efficiency of the system.
Yeah, I'm going to push back on that. Most of the power reactors in the United States and elsewhere they're like 50, 60 years old. But to say that no improvements have been made on those designs throughout that time period is wrong. Reactors are shut down every 1.5 to 2 years for refueling. New fuel designs are made. Power plants have been uprated, so the amount of power they generate has been increased over time. Their efficiency has been increased over time, like with that plot I showed earlier, their uptimes. Turbines upgraded and optimized, steam generators upgraded and optimized. So, I'm going to go ahead and, respectfully disagree with them there about that aspect, that traditional reactors cannot be, that are kind of, fixed in place. I mean, big things like the containment building or the reactor pressure vessel, those aren't changing, but, those just kind of sit there and handle certain stuff. The interesting bits, the fuel and the steam generators and the turbines, the stuff that, make your energy and heat, those have all been upgraded and are continuously upgraded and improved upon.
The reactor will be powered by enriched uranium in the core and contain thorium in the surrounding breeding blanket. The test is slated for 2026 and will run for up to 30 days at just 1% of the reactor's expected power output, but critically, enough to validate computer models.
No, I love to see it. I love the practical stuff. I just mentioned it earlier, but love to see the practical aspects and actually, putting the rubber to the pavement, as it were, and seeing the video of them working all these prototype reactors. That looks awesome.
Is on board, but there's no ski lift through the nuclear approval, and the pass isn't cheap.
I mean, one of the most expensive things are these licenses and approvals. I assume that once we have built more than 100 of these reactors, then the price of all this licensing and approval will also come down.
Once they build 100 reactors, so I mentioned it earlier in the video that the United States in its entire nuclear generating history has built just over 100 nuclear reactors. So Copenhagen Atomics expects the licensing costs to come down after they built 100 reactors. Hey, it's ambitious, man, but it's ambitious.
Neither China nor Copenhagen Atomics have demonstrated a true breeder reactor that produces more fissile fuel than it consumes. Copenhagen Atomics believes hitting that milestone, along with producing reactors at factory scale, could drive energy costs as low as $20 to $40 per megawatt hour, just a quarter of today's average for nuclear energy. To hit that price point, the company is reimagining not just the reactor, but the entire business model. It won't sell its reactors. Instead, it will build, site, operate, and eventually decommission each reactor itself, all without taxpayer funding.
So let's talk about, I hate to play Debbie Downer, but let's talk about a number that I think takes a lot of the wind out of thorium sales, and that is that the current cost of nuclear power, that's everything, the operations, the running the plant, all the people that work there. The cost of all that fuel is only 5% of that cost. So I think that takes much of the wind out of the thorium sales when you figure that, like, even if like some scenario that doesn't make sense where you can make fuel free, you're only reducing the operating cost of nuclear by like 5%. Granted, that's for traditional water reactors, but that's the model that we have established and that we can actually point to. There's nothing here for thorium molten salt reactors yet, so not to say it shouldn't be pursued, but I'm not sure that's the best argument to make for going after it. But it's interesting here that Copenhagen Atomics is going for this like vertically integrated approach here. So that means, they control, all aspects of the business. I believe X Energy here in the United States is going for a similar model where they kind of control everything. That's kind of like the Apple model, I guess, if you will, or something like that. So it's interesting to see that kind of business perspective. But where is this funding all going to come from if not from the taxpayer? Because this stuff is expensive. They kind of just gloss over that, but I don't know where that money is supposed to come from.
In exchange for taking the heat on nuclear installation, its clients will literally take the heat the reactors produce for use directly in industrial applications or for the conversion into electricity. The plan is to use the energy from the thorium reactions to produce hydrogen and ammonia. Electrification isn't always the answer, and nuclear reactors provide something solar and wind can't: ultra-low emissions heat for everything from producing ammonia and smelting aluminum to drying paper.
So this is the biggest argument for these small modular reactors and non-water reactors, in my opinion, is this what we call process heat. So, chemical plants like Dow Chemical, places that, just make plastic or refineries, they need a lot of heat because heat makes reactions go faster or even, take place in the first place. Chemical reactions, that is. Water reactors cannot do that. They do not provide enough heat. But these non-water reactors like TRISO pebble bed, high temperature gas cooled reactor, or this this thorium molten salt reactor. They can make their coolants can get really hot because they're not water based, so they can provide this process heat. And I think this is where these will make the biggest difference or make the most sense. Because when it comes back to like economies of scale and the siting requirements for nuclear reactors and all that, I still think big water reactors make the most sense for just baseline grid loading power, whatever you want to call it. And I think the niche for non-water reactors is really in like a process heat kind of space. Like Matt was saying, electrification is not the answer to everything. And yeah, I agree with that. You could even use water or non-water, reactors for district heating, and like in a cold place, you can heat homes with steam pipes from nuclear reactors as opposed to using fossil fuels or something. So heat, I think, is a big one. All right, guys, so that'll do it with this video. I saw this video got published probably a week ago now. By this time this video comes up, week and a half ago, and just utterly blew up. And I was like, okay, it's time to finally address thorium. So here we go. I hope it wasn't too much of a Debbie Downer. And again, I'm not against the pursuit of these technologies or the investigation of these technologies, but there's some aspects of it that need to be brought back down to earth a little bit about what thorium can and cannot do. But to be clear, my aim here is not to, hinder these efforts or stamp them out or, call people out. It's just to address some of these claims from a scientific perspective and, see what this technology can and can't do, and what it claims to do that other technologies can potentially already do, but just don't exist. So, thank you guys for watching. I hope you guys enjoy this, and I'll see you guys next time.